Okay. So first of all, I would like to welcome everyone, and I would like to thank to our distinguished guest, and who is joining us to actually celebrate for the International Day of Women and Girls in Science. And since we are close by to the International Women Day, so this is very important for us because today we recognize the vital contributions of women in science and inspire the next generation of female scientists. Since sciences thrives on diversity and history is filled with the remarkable women who have shaped our understanding of the world, it is our pleasure to welcome Professor Catherine Frees, who is a distinguished physicist working on dark matter and who has made significantly advance in astrophysics. So, welcome, and I would like to leave the floor to you, and I would like to thank you for joining us and for this special event. And welcome to Professor Catherine Fries. Please, floor is yours now, and you can share your slides.
Okay. 1 second. So let me now
Yeah, now
put
we
in
can.
present.
Yeah, well, it would be better if you can. Yeah, great. Yes, perfect. Thanks.
Oh, yeah. So I did want just now when you were speaking, it was a little bit glitchy. So if I am glitchy, please let me know so that I don't just keep talking and you know what I mean? So
Well, your voice is perfect for me, and I don't have any problem. It's very clear.
wonderful.
Yeah,
Okay. Um, so I should speak for half an hour or so. Is that good?
yeah, that would be perfect indeed.
Great. Let me introduce myself first in terms of where I'm working. So I'm at the University of Texas in Austin, and I'm the director of the Weinberg Institute for Theoretical Physics in honor of the late Stephen Weinberg, who his office was 3 doors down from me, and one of the founders of the Standard Model of Particle Physics. So very indebted to him. I'm also a professor at Stockholm University, and in Stockholm I was also director of NORDITA in, I guess it was 2014. So then let me move on to, except that the slides are not advancing. That's interesting. Okay, I
Uh,
got it. So, I want to do a basic introduction to the modern field of cosmology. If you think about it in human history, people always, I'm sure they always ask questions about who we are, how we fit into the bigger picture. They had creation myths about where we came from. And the thing that's so incredible about our era of humanity is that starting from 100 years ago, the brilliant insights of Albert Einstein in 1915, we have our own story, a creation story called the Hot Big Bang. And the difference is that it is actually correct. It is incomplete, but correct. That's really remarkable in human history. Another thing that's remarkable more recently is that for most of the history, even as of the last 100 years, it was white men, and before that, they had to be independently wealthy white men who did all the science. And in the recent past, it's become a career accessible also to women. And I was actually the first woman hired at the University of Michigan as a professor of physics. And so this field is growing in terms of the participations of women in the field. Let me turn now to the science. And so, as I said, it's all began with Albert Einstein's relativity in 1915. Then others applied the theory to the universe as a whole and realized that those equations had several possible solutions for the universe, expanding, contracting, or static. Einstein liked the idea of a static universe, which would be the same at all times. He liked the idea of this additional symmetry, but that's just not the real world. In the 1920s, it was Edwin Hubble who used the telescopes above Pasadena to make several astonishing discoveries. One of them is, well, at the time of Einstein, the theory was way ahead of the observations because even then people were assuming originally that all the bright stars in the sky that we call the Milky Way and beyond it, that everything was within our own galaxy and that there was nothing else. Hubble looked at light from some of these distant objects and proved that they're too far away. They have to be from galaxies beyond our own. So that was a major discovery. A second major discovery was the expansion of the universe. And the way he did this was looking at galaxies at various distances from Earth, and the light waves are stretched by the time they get to us. If you look at it on a balloon, you draw a wave, and then as you expand it, then the wave stretches. So imagine you know what the wavelength is at the time. These are the wavelengths from stars. You know what they are at the time they're emitted. And then by the time you observe them, they're stretched. And the reason is the expansion of space. Einstein had to abandon the static universe. We do live in a expanding universe with everything moving apart from everything else on large scales. You and I are not moving apart from one another. Well, sometimes we are, but the galaxy is self-contained because gravity is stronger than the Hubble expansion within our galaxy. The general story, the picture of the hot Big Bang is that the universe started 14 billion years ago in a hot primordial soup of particles, quarks, leptons, photons, etc. And these were very, very densely packed together. The universe was very, very hot. Since then, as I said, the universe has been expanding, and also in the process, it's cooling off. Here's a picture of an analog raisin bread. Here we have raisins inside this bread, and you can think of the raisins as analogs to galaxies in our universe. As this dough is put in the oven and the raisin bread expands, by the way, I'm not a cook, I've never done this, but it makes sense that the raisins move apart from one another, not because they're doing anything, but just because the underlying raisin bread is expanding. It's a good analogy for the universe with one exception. The raisin bread has a central point, and we do not think the universe does. In fact, we think those are the symmetries that are built into the original equations for the evolution of the universe, that there's no special point in the universe. I also wanted to talk about the notion of a Big Bang, which most people and the public and public press presents incorrectly, which is, all right, let's start from today and go backwards in time. Okay, if you do that, everything gets closer and closer together, the opposite of expansion. It's a contraction. Everything in the room I'm sitting in would contract to a point. But let's say the universe is infinite, in which case, although things get closer together, there's still infinity remains infinity. So there's still stuff way outside. So you're not contracting the entire universe to a point. Instead, what happens is the density, the number of particles in any volume gets so large that our laws of physics fail as we know them. And we don't have a theory of quantum gravity, maybe string theory. We don't know what to do, theoretically speaking. That is the Big Bang. So it's not a point in time. Sorry, it's not a point in space. It's a point in time. There's not really an explosion either, but let's put one everywhere in space at the original time of the Big Bang. Let's turn now to this question of what the universe is made of. And it starts with a remarkably surprising fact, which is, let's take all the objects of our daily experience, our bodies, our chairs, our walls, the sun, the earth, everything that we're used to, the air that we breathe. It's all made of atoms, which are made of quarks. And all of that adds up to only 5% of the content of the universe. In fact, here's a pie picture of the universe. Here's the ordinary stuff. Everything in our daily lives is in here in the 5% of the universe. Roughly 25% dark matter and 70% dark energy. which leaves us these questions. If these things dark just simply means they're not giving off light, probably not related to each other, two different components. And what are they? We can observe their action on the universe. We don't know what they're made of. In fact, the dark matter problem is now 90 years old, dating back to Knut Lundmark in Sweden in 1930 and Fritz Zwicky soon after. Here is Knut and here's Fritz. Fritz famously was studying a cluster of galaxies, it contains hundreds of clusters, and he observed the galaxies moving around the center of the cluster. Well, you'd expect those orbits to depend on the mass in the other galaxies, but it didn't add up. The galaxies on the outside of the cluster were moving really, really rapidly, and that so rapidly that unless there's that they should be just spinning off. They shouldn't be contained inside the cluster. They shouldn't be bound to the cluster. So what the implication is, there's additional mass in there that's grabbing onto those outer galaxies and keeping them in orbit around the cluster. The proposal was dunkle Materie as the explanation. He was a Swiss scientist, and again, dark matter just means it's not stars, it's not shine, it's dark. I have to tell a story about him, which is that in his book, he called his colleagues spherical bastards because no matter what direction you look at them from, they're still bastards. Let's see. Well, that story of the original proposition of dark matter, there was a pros and cons and different observations and blah, 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 but it was really the work of Vera Rubin in the 1970s that clinched the situation. She showed that all galaxies have dark matter in them, which led to the scientific consensus that dark matter is really there, and we have to figure out what it is. I'm going to show, in order to explain what she did, an analogy. Forget about dark matter for now. Let's go to the solar system as an analogous system. And what I've plotted here is the average speeds of the planets. All right, this is called a rotation curve. So this axis shows you how fast the planets are moving, and this axis is the distance of their orbits from the sun. Okay, so the fastest planet is the one closest to the sun, Mercury. Then we get Venus, Earth, Mars, da, 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 da. The farther you go away from the sun, the slower that the orbits of the planets. Their speeds depend on two things: the mass of the sun and the distance from the sun. So if the mass of the sun were 4 times as much, all the planets would be moving twice as quickly. And for fun, Tycho Brahe was one of the people who made the observations of these planetary objects in orbit around the sun. And he lost his nose in a duel and wore a gold and silver replacement. Then he also, this is a fun story that I thought I would tell, which is that I'd always heard that he died at a dinner with the king because he had a lot of wine, but you're not supposed to get up. This is in Denmark. You're not supposed to get up before the king does. So his bladder burst and he died several days later because he didn't. But then there was a competing story that Johannes Kepler poisoned him with mercury poisoning, and that's why Kepler's laws are called Kepler's laws instead of Brahe's laws. What they did a couple decades ago is they dug up his body and tested his mustache hairs for mercury poisoning. No evidence. So I guess it's true that he died of a burst bladder at a dinner with the king. I was at a dinner with the king, and let me tell you, they were not happy that I had to get up to go to the bathroom, so I believe this story. Okay, then let's get back to dark matter now. So this is a similar, in terms of the orbit, similar story to the solar system. This time we're looking at a galaxy, and we're looking at some object, star or gas or whatever, moving around the center of the galaxy, and its speed is determined by the amount of mass interior to that orbit. So this is the same equation really, but the difference is that instead of just having the mass of the sun speeding it up, it's the mass of everything inside this red circle that speeds it up. If you have more mass in the middle, then these orbits will go faster. So then here's the kind of thing that Vera Rubin found, which is, again, this is again a rotation curve, the speed this time of stars moving at a certain distance away from the center of the galaxy. This is the radius of the orbit. If you only had the stellar material inside the galaxy, then this is what you would expect. Just like the solar system, it would get slower as you move out. But no, this is a flat rotation curve, is what it's called, which means things are moving too quickly. What you have to do is add an additional material. If you add in this dark matter halo, then that would explain those rotation curves and why things so far out from the center of the galaxy are moving rapidly. Well, a nice example is our Milky Way. And at the center here, we have a supermassive black hole, and it weighs 4 million times as much as the sun. Getz and Gensel got shared Nobel Prize, well, half of it, for the discovery of this supermassive black hole. And they found it, this is artist rendition, by observing stars moving around the central black hole. And there had to be a giant mass in there to speed up, same idea, the orbits of the stars around the black hole. Okay, so our galaxy then, as you move away from the black hole, has spiral arms of structure. Here's our sun. And the stars are all in this, if you take this and you put it on the side, that's where most of the stars are, in this flat thing that we call a disk. The sun being 25,000 light years away from the center. Okay, so that's the disk of the galaxy. But now let's put it, oh, by the way, supermassive black holes are not the dark matter. Every galaxy has one, but they only make up a tiny fraction of the universe as a whole. Let's get back to the Milky Way. This is an artist's rendition of the spiral structure of the disk. But look at this giant black, we call it a halo of dark matter surrounding this galaxy, and it's needed to stabilize the galaxy. Well, that was the first way dark matter was found, was from these rapid motions of things in orbit around the centers of galaxies. Another way to do it is to use Einstein's gravitational lensing. This is a weird phenomenon that mass bends light. If you have any dark stuff here, for example, massive compact halo object, whatever that dark matter is, it doesn't give off light, but it bends the light behind it. So the light from a distant star would bend on the way to our telescopes. There's no kink here, it's just my drawing. And so you'd see the star over here instead. You'd think it was over here, but then you'd also notice two effects. One is this is a very distorted image. And secondly, there are multiple images, identical images of the light coming around different directions around the dark stuff. By looking at these distant stars, you can figure out how much dark matter there is and where it is. On your iPhone, there's an app created by a University of Michigan grad student, Eli Rykoff, and it has the correct equations of gravitational lensing in there. And so you can lens yourself more and more and more. This was my student. Let's get to some real data from Hubble Space Telescope. Well, look at this. You certainly see these sheared images. There's multiple images. This is a very rich image with a lot going on. I don't know all the details. But from these images, you can reconstruct the mass that was required, the dark matter en route between the distant galaxies and us. This is from a different Hubble Space Telescope image using a computer to reconstruct the mass. Here's the mass that it took to create one of these images. And what you see here, this is a cluster of galaxies with, you can see these galaxies making these density peaks, a lot of mass in this. This is in space. You have a lot of galaxies here, but additional dark matter in between the galaxies. So clusters have even more dark matter in addition to what's inside the galaxies. Third piece of evidence for the existence of dark matter, the famous bullet cluster. Here we have two clusters that hit each other. They collided. And what happened? Well, the atomic matter, if you and I collide, we're not getting very far. We have strong interactions. We have electromagnetic interactions in between us. So we get stuck. So this is gas giving off X-rays shown in pink. That's how we know it's there. But there's an obvious difference between the way the gas reacted and then the way this dark matter did. This is also found by lensing, shown in blue. The different types of mass, the normal atomic matter and the dark matter, behave differently. The dark matter just keeps right on going. It does not have the electromagnetic interactions or the strong interactions. Strong interactions hold our nuclei together. I think I'm going to skip ahead or just go through this very quickly anyhow. So if we, in the creation of galaxies, starting from somewhat lumpy dark matter, getting more and more lumpy until you eventually end up in today's universe with filaments of dark matter. And at the nodes, the intersections of these filaments, you have galaxies. And galaxies would not have formed yet, wouldn't have formed quickly enough unless the dark matter clumped first. So we need dark matter for us to exist, for our galaxies to exist. So I've shown some evidence for dark matter. One of the biggest ones is actually from the leftover light from the Big Bang. This is created, the photons, particles of light, stream towards us from 400,000 years after the Big Bang, and the behavior of that light absolutely tells us dark matter has to exist. So I haven't had a chance to talk about that as well. But there's evidence all over the place. Dark matter exists. The question, of course, is what is it made of? One of the earliest things that you might try would be gas or snowballs of hydrogen or rocks or dust. But the trouble is, those were ruled out a long time ago because they have observational consequences that just don't work. Then what we are in the situation we are in today is that people have proposed a plethora of ideas for what the dark matter could be. I've listed some of them here, including the top two are the most theoretically motivated ones. But I do want to say, well, neutrinos, they exist for sure, and that would have been so great if they were making up the dark matter, but they don't. First of all, they're really light, so they ruin galaxy formation, and recently we have been able to measure their masses, and they are just too light. So they make up 0.5% of the universe, not 25%. And they stream out of structures instead of causing them to clump. Other possibilities would be a new type of neutrino, sterile neutrinos. Primordial black holes are particularly interesting. Florian Kuhnel was a former member of my group. And what are primordial black holes? Well, they would have been born in the very early universe when there was some kind of phase transition, the inverse, like water boiling or the other way around, that's a phase transition. And then that's where you would have a lot of matter clumping in small spaces, collapsing to make black holes. The reason people are excited about this is that it's possible that the detection of gravitational waves by the LIGO detector, what they see is merging black holes, and those black holes could be primordial black holes. I have some slides on gravitational waves, which I don't really have time to discuss, but it did lead to a Nobel Prize in 2017. Just it's an amazing experiment. But I want to jump ahead to the candidate I've worked on mostly, which is weakly interacting massive particles, or WIMPs. A reporter once asked me, so we figured it out. Billions pass through your body every second, between one a day and one a month. Hits one of your nuclei, but obviously doesn't do anything to you. Well, because you're surviving the experience. So we do know that they don't have strong nuclear forces, don't have electromagnetic forces, which since they don't give off light, they can't. Yes, they feel gravity. Now, these are three of the fundamental forces. The fourth one is weak interactions, which are responsible for some types of radioactivity. Let's make the postulate that dark matter, the only interaction it feels besides gravity is the weak force, and then it weighs 1 to 10,000 times as much as a proton. That is a WIMP, weakly interacting massive particle. We're interested in them for theoretical reasons, for two theoretical reasons. One of them is if you calculate in the early universe, they're their own antimatter, they annihilate with each other, and how many are left today, you get the right answer for the dark matter, okay? And that's reason number one is some people call it the WIMP miracle, you get the right numbers. The second reason that they're so highly motivated theoretically is particle physics is incomplete, there are problems. In solving those problems, people propose supersymmetry, leading to doubling the number of particles. These supersymmetric particles are unstable, except they decay to the lighter until they get to the lightest one, which is stable. It could be the dark matter. Those are the two reasons that we like the idea of WIMP detection. Now, there's a three-pronged approach to looking for it. That is to make it, shake it, or break it. I hope I have a little time to talk about the fourth prong, dark stars, which is my baby. But let me just say, one way to look for WIMPs is at the Large Hadron Collider at CERN there's a 17-mile ring where protons are accelerated in opposing directions and smash into each other, possibly creating supersymmetric particles or dark matter, but that has not borne fruit. Nothing found yet. Second way, this is an idea that I was one of the pioneers of, underground direct detection laboratory experiments. All right, so here you have detector made of some nucleus. You have this enormous number of WIMPs in the galaxy, as I said, billions going through your body every second. When they hit the nucleus, the WIMP hits the nucleus, scatters off of it, and it heats up that nucleus. And people are looking for that. How did I get into cosmology? How did I get into studies of dark matter? It all started with my PhD advisor at the university, David Schramm. This is a picture of us back then. He was one of the founders of astroparticle physics, an incredibly inspiring human being. His nickname, because he was an Olympic hopeful in wrestling, Shrambo. Unfortunately, he died flying his own plane at age 52, but he was really one of the creators of this field. All right, so that was me in grad school. Then here's me as a postdoc at Harvard, and together with Andre Druckier and David Spergel, we wrote some of the very earliest papers that propose. I calculated interactions. What happens when the WIMP hits the nucleus? What are how often does that happen? And so we made predictions that led to the founding of this field of underground laboratory detections. And you have to go underground to get away from competing cosmic rays, which there'd be a million of those for every WIMP, but they don't get through the Earth. So this is an example of one of these experiments. It's a worldwide effort, and again, no success in discovery yet, which is frustrating as can be. New ideas that we have: digging up ancient minerals from deep underground as a cheaper alternative that they've been collecting tracks for a billion years. Got to show this picture. Dark matter is a field, a lot of women in the field of dark matter, and here's a bunch of us at one of these meetings. Then I'm not going to talk about indirect detection because I'm out of time, but I will say I do want to mention dark stars. This is something I'm super excited about right now. The idea is that the very first stars that form, oh, this is just fun. This is my collaborators. The very first stars to form in the history of the universe would be made of ordinary hydrogen almost entirely, okay? Almost entirely. Dark matter constituting less than 0.1% of the mass of the star. But that same dark matter annihilation I was talking about can power the stars. There's no fusion. These are very cool, weird objects from way, way back. And I have plenty of slides on this story, but they can grow to be really, really big. 10 million times the mass of the sun, and 10 million, a million times the mass of the sun, and 10 billion times as bright. How weird. Their radii are 10 times the distance between the Earth and the sun. And the point is, if you've got an object that bright, well, before I get into that, what happens when they die? Well, then they become supermassive black holes, which is a possible explanation of these very hard to explain supermassive black holes, even in the very early universe. But let's get to the James Webb Space Telescope, because they could observe these very early, very bright objects. And what we're excited about, that we have candidates in James Webb data. That's so, yeah, anyway, so they match. Let me back up. JWST has a lot more than 700 now, bright objects from the early universe, which they're assuming are galaxy candidates, but that would be too many for the standard model of cosmology. Okay, maybe some of them are dark stars, because one dark star can be as bright as an entire galaxy of early stars. And so that's my basic bottom line there, is that maybe they've been found in the James Webb Space Telescope, and we need more data to confirm or deny that. Well, I talked about different mechanisms of going after WIMPs, the underground experiments, collider searches, looking for dark stars. And I'm going to end on a joke. Well, I didn't say anything about dark energy because it's a really, 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 really hard problem, but I do want to tell you how it's different from dark matter. And the difference is that the definition of matter, and that means all of these, that means ordinary and dark matter, is it feels gravity. So it's gravitationally attracts. You put any of these particles together, they're going to attract each other. Dark energy does the opposite. It's repulsive. It's it was a shocker and around the turn of the millennium that it seems the universe expansion is it's not just expanding, but it's accelerating, which means all this picture of these galaxies moving apart from one another on the average, they're accelerating apart from one another. And that was really not expected. The, the on the theoretical grounds, we're really stumped as to how to explain that. On observational grounds, there is some interesting data that maybe show that argues right now that acceleration changes with time, but we don't know. But I'm going to end, as I said, with a joke. The three of us here, this is at the World Science Festival in New York. The three of us here were talking about dark matter. These three guys about dark energy. And I made a joke based on the only thing that we know to be true about dark matter is attractive. Well, dark energy is repulsive. So I hope this is the dark matter people, and these are the dark energy guys. I also, in case you're interested, wrote a book for the public called The Cosmic Cocktail, 3 Parts Dark Matter. And here's my recipe. And I think that I will end on that. So let me stop sharing. And I think I did 29 minutes. Wow, pretty good.
Yeah, it's perfect. Wow, you are perfect. Thank you very much for this nice overview and let me check if there are any comments and questions from our audiences.
I have another one more comment. I usually do talk about axions, which I didn't have time, in which case I always show Luca's work because he's got, if you're interested in axions, look at he's got amazing reviews out there.
Oh, okay, thank you.
Thanks.
I don't see, but okay, let me, well, since I'm a particle physicist and working at CERN as a CMS experiment member, I just would like to get your opinion about what role of the particle physics can play in advancing our understanding of the dark matter and dark energy. Although you have already reserved one slide, but maybe you can give some more ideas of what do you think about this?
Well, it's too bad I don't have the backup slides because I didn't think I'd need them. Well, can I find them really quick? Can I find something really quickly? Maybe not. Whoops, it doesn't help if I open the wrong thing. I would like to show a slide actually, if I could. I can get there pretty quickly, so give me 1 second.
Yeah, sure, please take your time.
Okay, so I am going to share screen again if I can. Whoops. I have to get to the right window. Okay, there we go. Give me a second. Damn it. I'm trying to move things around. Okay. Okay, so back on this question so the answer to your question is twofold. One is the experimental side.
Yeah.
At CERN, the two detectors that are useful for the two main detectors, I shouldn't say some of the others are too actually, but Atlas and CMS, which you refer to. And always fun to show these pictures. There's Peter Higgs at the CMS. I guess you're working on CMS?
Yes, I am the member of the CMS experiment.
Wonderful. Well, so the LHC did discover the Higgs at 125 GeV. If you ask people beforehand, other than just any new physics, what they thought, I asked this to David Gross one time. He goes, SUSY, SUSY, SUSY. So supersymmetry, you'd have proton collisions creating supersymmetric particles, which would then go along a chain, decay in a chain until you get to the lightest one, which would escape detection. And this could be a candidate for the dark matter and lead to missing momentum, missing energy. The second signature would be these ordinary particles coming off in jets. So you could look for the right combination of these things. Nothing's seen yet, which means, well, that's a good question, but it does mean things are being pushed to higher masses. This is an ancient plot from Atlas, but the basic story hasn't changed, so it doesn't matter. If you assume that the instead of having 105 free parameters, which even the minimal supersymmetric standard model does, you unify things by having all fermions at high scale be the same mass and all bosons at high scale be the same mass. And then you run those masses down to get a variety today. If you make this unifying assumption called MSUGA or CM constrained MSSM, then you have only 5 free parameters and you're able to make plots. Okay, so if you do that, that rules out that you have to be at higher masses, you have to be above all these lines. And as I said, it's gotten more constraining. So we're talking TeV scale now. But I wanted to comment on that a little bit. First of all, as we knew before the LHC ever started, even it may miss supersymmetry. Supersymmetry could still be there. We knew that. And then you'd have to argue for a higher energy accelerator, which gets more difficult if you haven't found anything at the LHC to motivate that. So yes, it could be at high scale, or it could simply be that this unification I'm talking about is too simplistic, that you have to open up the parameter space, in which case lower mass stuff is still available. Oh, another comment, even if supersymmetry is found at the LHC, you still don't know how long-lived those particles are. If they're escaping the detector, doesn't mean they live the age of the universe. You have to do something, other approaches to prove that it's dark matter. Okay, so that was on the experimental side. I thought those were useful slides. And then on the theory side, let me go back to this. I don't know where I have this list of potential dark matter particles, but a lot of people are working on a lot of ideas from on the theoretical side. In addition to, I talked about WIMPs, but there's and primordial black holes, but on the particle theory side, there are a million other possibilities. This is just some of them. There's also, for example, self-interacting dark matter, which is motivated by looking at density profiles in galaxies and other problems, astrophysical problems that maybe means that you have a new type of dark matter. There's also dark photons. If you have an entirely new dark sector that communicates with us, with our sector, perhaps through a kinetic mixing or in other ways, and so people are searching for dark photons as dark matter. Then a very popular subject now is light dark matter. WIMPs are heavier than about the mass of the proton, 1 GeV. But people are interested in going much lighter than that, all the way down to 10 to the minus 22 EV, at which point the dark matter would no longer be, it's wave-like down there. It's no longer really confined to the galaxy. Asymmetric, there's a ton of candidates that people are talking about. I'm particularly interested, I guess, sterile neutrinos, I think, are very interesting. I mean, the neutrinos have mass, and so how the heck can you explain that? You've got to do something new, and having a fourth neutrino species helps with that, although those heavy sterile neutrinos are not the dark matter. But anyway, so I think sterile neutrinos are particularly interesting. Some people claim there's hints of discovery of that. I also think that primordial black holes are very interesting. A lot of these are very interesting. Self-interacting dark matter they're all very interesting. So anyway, I hope that is somewhat of an answer to your question.
Yeah, thank you very much. So I don't see any other questions on this side, but now I would like to come to the point that since you have many experiences as a women scientist, and I would like to ask, and this is a special event actually we reserved this event for celebrating International Girls and Women Day. So I want to ask one question. I think it was a big challenge for you to be a woman in a man-populated environment. And what was the biggest thing that, the challenge you faced on your career, for example? Um, Maybe you can, I think you have many
Yeah.
challenges, but you can pick up the biggest one probably. This is really very important.
I don't know. Oh, there are so many. I don't even know. But one of the biggest ones is it's better now. But I arrived pregnant at MIT as an assistant professor, okay, because they were at that time they said if you're over 35, you can't have children anymore, so I was in a hurry. That was that was an experience. MIT is a pretty was it at the time, I don't know about now, an extremely macho environment. Even the buildings are kind of macho. I found that I like the buildings actually, but and so that was really difficult. The the most difficult part was that maternity leave didn't exist. I was told by the chairman that a maternity leave is the benefit that MIT cannot afford. So I was teaching for the first time in my life with a baby. And on top of that, there was no childcare. And in all of Boston, you couldn't get childcare. We paid $900 to some agency. Imagine at the time that was a lot of money. And the woman they found us quit. And so we were desperate. What the hell are we going to do? But her friend took the job. It was an Irish nanny. And my husband at the time was a postdoc at the Harvard Center for Astrophysics. And 100% of his salary went to the nanny. Okay. And so I actually cried about money every night. And then my father's mother died, my grandmother, and left us $50,000, which enabled us to survive the 3.5 years I was assistant professor at MIT. So we had to move somewhere cheaper. And Michigan luckily took both of us. And that was anyway. So nowadays, everybody gets parental leave, men and women, because they don't want to seem unfair on the whole. Women's bodies taking the toll of pregnancy doesn't seem to count. So everybody gets parental leave, which is actually, I think, is wonderful. That is, that women aren't stuck sitting at home all the time or whatever. So it works out much better now. That's an improved situation. However, going to the office and having people look at you like, why are you shouldn't be here? That was the other one. That was
Oh,
really scary.
yes, indeed. And
Very unpleasant, I can tell.
since I mean the in the science and technology and engineering, it's okay. Nowadays it's getting better actually, but it is still the man-populated environment. And do you have some suggestions or some opinion about what you can give an idea about to create more spaces for women? What can be done, for instance, uh, according to your experiences?
Well, I don't know how many young women are in here, but that the mentorship is really valuable. So the PhD advisor I did end up with, I transferred schools and many times until I found the guy that was really the right one for me. And so finding a good mentor is absolutely essential. Um, and well, that's true all the way up the line. If people help you, that makes a big difference. And you shouldn't, I don't, help is the wrong word, but they mentor you. The other thing I can say is that women tend to not believe in themselves. I always thought, well, I don't really, because I was made to feel I don't belong here, so I believed it. And I thought, well, I'll just keep doing it and eventually I won't get another job. And I'm not as smart as these guys and da 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 da. But, in high school, I thought I was um, a, kind of like a genius or something, I'm embarrassed to say. But then actually, after 1 year of college, I also went to MIT at 16 as an undergraduate. By the end of that year, I thought I was stupid. The truth is somewhere in between, probably closer to what I thought when I was 16 than when I was 17. Not that I'm a genius, but that I'm pretty smart. And it took me decades to rebuild my self-esteem. And now I can just be myself and feel comfortable. And I do think that the US is particularly bad in this regard. And so European women, in my experience, don't suffer from this. They're not beaten down by the time they're 17 years old. But believe in yourself. You can do it. If you're succeeding, it's not by chance. It's because you're actually good at it.
Yeah,
Those would be
actually,
two pieces of advice I would have for
I was
people.
about to ask you what kind of barriers, the biggest barriers from women's side that I mean actually you have just answered my question, like to believe in self, in self, women has to believe in herself. and not
Yes.
to prepare it. I think it's the biggest barrier for the women who do not believe themselves, and we really don't think that in the men populated environment. Sometimes I feel also that I'm not that smart enough, and the people force you to believe in this.
Yes, I hope you know better intellectually, even though emotionally it's hard to move past that.
Yeah, it
But
is.
if you know it intellectually, right?
Yeah,
That you're smart enough.
yeah. Um, okay, yeah, that's well, your opinions and experiences are very precious for us actually, and thanks a lot for sharing your opinions and experiences. Oh, let me check
Well, I
if
am sorry that the timing is late in the evening for you, so that but thanks
no,
for being here.
it's a big pleasure for us to welcome you in such an event, and it's a great thing for me actually. I'm very honored to meet with you in such an occasion actually. So, and I see that people are sending heart to you, I think. Yeah,
Oh, thank you, thank you, thank you, thank you. And thank you for making this happen. This
yeah.
is awesome.
Yeah, you are one of the motivating person for the women, actually, women who are in the science. You are really well motivating us because the idea to invite you. We have a group actually. We are in a cost.
Please tell me about yourselves. I'd be interested to hear about your group.
Well, this is actually a project, and it's provided, well, it's funded by the European Union, and I think, Alessandro, correct me if I'm wrong. So it is a national, not the national, but international wide, and many people can join. And the action chair, it's called action actually, rather than, so the action chair is Alessandro Merizzi. And so I am, well, representing the gender and balance advisory of this project. And okay, together with the science, we are trying to also to enlarge our knowledge and, to awareness of the gender balance, diversity. These kind of concepts are important. So, and we have a committee now in our cost action. There are three more ladies joining with me, and we just came up with the idea we should invite somebody who is, who can really inspire us and motivate us, and not all us, but also the other ladies who are just, joining to the science or engineering or other subjects. So, and we were thinking about, yeah, and we were asking,
What field are what?
okay, I'm a
Oh, I'm
physicist.
sorry. I just was curious. What field? Mhm.
Okay, sorry, ask it again. I couldn't hear
No,
you.
but I mean the group. How broad is the group?
The group. Oh, okay,
How broad
Alessandro,
is the
maybe you
group in
can
terms
comment
of
on that. The
field?
road. We
Yes, so now we are about more than 400 people, 450,
Wow.
and essentially we represent mostly the European community working on actions that photons, so what we call WISPs, so the light particles that could be the dark matter. So we are a network in which there are both theorists, astrophysicists, experimentalists, and essentially what we do with this action is to organize workshops as a training school for young students, and
Oh
also
no,
we
no,
have.
tell me. So wait a minute. Did I talk at way too low a level for this group?
No, no, no. I mean,
no,
it was
no.
intended also for. I mean, because what was mostly interesting for us was your experience as a woman in this community of dark matter and astroparticle in general.
I see. Okay. Well, I guess I did talk about that to some. By the way, if I forgot to say it, one of the best candidates are are axions. I did say that, but I
Yeah, yeah,
just
but you put in your slide.
Yeah.
okay, good.
Okay. So I don't see any raised hands, any questions, comments. If you have, please, the audience, speak up. Otherwise, uh,
I have
Yes,
a very small comment,
yes,
maybe.
please.
Let me turn on the camera. Um, well, hi. So I've been a student of Katie during my postdoc ages. Katie is inspiration for everyone.
Oh,
In this,
Luca, thank you.
it's true.
Luca, by the way, let's congratulate Luca. He has a new position in Italy. Tell us about it, Luca. I'm excited for
Uh,
you.
well, yeah, I'll keep it just to the focus of today because I
Yeah.
think it's really important, not just for everyone, not just from the 50% I don't belong to, but the other 50%, like males, also have to learn how to deal and work together. So this is a very delicate topic, and I think that the active participation of everyone in this initiative is quite important, and we are far from a real balance in terms of duties. I see myself because I'm a man, but I interact with colleagues. I train students, might be females as well. So I deal with the other 50% of the population as well. And I think of myself like 10 years, 20 years back, and I thought that like I grew in terms of interactions, and there are some mistakes or small mistakes that I might have made back in the past that I try to correct. So, and this is common for everyone. So we learn from our interactions, but also from what we hear about stories. So I think this is the important part of this not just this day, but of our daily routine. And this day should just be a memorialization of what we should try to do every day to improve ourselves. So thanks.
Thanks a lot, Luca, for
Mhm.
your comments. So,
Mhm.
um,
Yeah. Okay. Thanks, Katie. Okay.
Thank you, everybody.
I don't see any other person.
Thank you so much for joining us.
Yeah, thank you very much, Catherine. It was a really pleasure for us to, and it's a great honor for me to welcome you in this nice occasion. And maybe sometime again we will be inviting you for some other events, and you can then talk about more, details of the dark matter and energy and also all your recent babies, let's say, baby topics. So thank you very much. And I think we can close this session. And I really, really very much appreciating to welcome you here, and thank you very much. And
Well,
have a
thank you. Really nice to meet you all. And yeah, this was a really nice event. Thank you so much.
thank you, and have a nice day, and have a nice evening, all the other people. And okay, take care and bye bye.
Thank you, Dennis, for
Thanks.
organizing this.
Yes, thank you.
Bye bye, Catherine.